Recording. Okay. How visible is that if I don't put the slide down? Yes.
So I had a little bit doubt. So let's say for this quiz or for any other test in the future, is there something called error carried forward that we used to have in school? Basically, if one of the subparts you mess up and get the wrong SF and your answer is wrong, and you use that in another subpart and all your subsequent answers become wrong, does that mean all of your answers are wrong?
No, I give lots of partial credit. Okay. However, I always reserve some small fraction of the points in any one problem to whether or not it's just plain right. Okay? So you won't get that part. But if all the work is consistent, you'll get most of those points. Okay? Yeah, I'm going to say some more words about it when we start here in less than 2 minutes. In that little seminar room right across there. Okay, it's 8:20, so let me start class like I will normally do with some announcements. Again, these are just meant to help you make sure you're on track, know what's coming up next, and when kind of manage your time so that you get things done when they are due. So you had homework due last night on Wiley Plus. Those were our first homework problems in chapter 2, motion along a straight line. If you've been on Wiley Plus since then, you'll notice the next set is now available, and it will be due Monday night. And then the next set will be due Thursday night. As I said, it's a pattern, okay? We, of course, our next class will be Monday. I will be sending you an email with a link to the video lecture for Monday. Really important, again, to watch the video lecture before class, because I build from there. I don't repeat all that I say in there during the class. Okay? If anybody hasn't turned in their lab reports, please do so today. Okay? I need to get those graded. Those are handed back the next time lab meets. Remember, lab is experiment 2 next time, and that you need to read that experiment before coming to lab, and you need to read that section on data taking and uncertainty analysis. It's pages 7 through 14. You will need that content to do the lab next week. I'll say that again in Monday's class. Okay, so the last announcement is probably foremost on your mind, the quiz. Remember, there's a quiz today. We're going to run it like a mock. That is to say, the points are only going to be bonus. So if something goes wrong and you forget or whatever for this first quiz, it's not the end of the world. But I wanted to run it exactly like we're going to do it from now on so that you know how it's going to work. Okay, here's how it works. The quiz is on Blackboard. You'll find a folder that says quizzes and tests. All right, you open that. It'll say quiz 1. It will not become available until 9:30 this morning, Eastern Daylight Time. Okay, it will be available at that point. You don't have to start it then. That's when it's available. Very clear so far. All right, when you've got a chunk of time where you can sit down and do the quiz, when you're free, sometime today, go in there and open it. The minute you open it, just so you know, a timer starts. You have 2 hours to do the quiz and turn it in. To do the quiz, you just open the file. It's a PDF. You read it. You do all your work on blank paper. Okay? Let me make clear what the rules are, because we all must abide by them. So as I said, you have 2 hours to complete the quiz from the time you access it on Blackboard. The quiz will be available from 9:30 this morning until 11:59 p.m. That means you have to get it turned in by 11:59. You can't start it at 11:58 and think you're going to get 2 hours. You understand what I'm saying? Okay. You are to do all your work on blank pieces of paper, organize and label your work clearly, so that if you're doing part 1 or 2 or 3 or 4, your work is all labeled. All right, any mysteries, and I'm not likely to give you partial credit. Okay. Lined paper is okay. Lined paper is okay. It's coming. Okay, but that's a good question. When finished, scan your work and create a single PDF file, please. One PDF file that you then upload there at the Blackboard site where the quiz was. Okay? The quiz is open book and open notes. I'm not interested if you can memorize things. To a physicist, memorizing is not really that important. Now, open book means Wiley Plus, our Wiley Plus site. That's the book. Anything on the Wiley Plus site, you are allowed to refer to. And open notes means any notes that you take in our class, Okay, is that clear? All right. Of course, you may also use a calculator. All right. Here's the important part. No other resources are allowed. None of any kind. Just to be clear, you may not talk to anyone about this quiz or ask anyone for help. You may not look at anyone's work. You may not refer to any other books or any online materials whatsoever other than Wiley Plus. Okay? And any violations of these rules is academic dishonesty. Now, here's the way we're enforcing this rule. It's on the honor code, so let's not have anybody violate it. On the first page of your work, not only do you write your name so that I can read it, but you sign it like a signature, like on a check or on a legal document. And by signing it, you are saying to me, I have followed these rules. Everybody clear on that? I will not grade the quiz if that is not, signature is not there. Because I take that lack of a signature to mean I didn't follow the rules. Okay? So I'm not putting any pressure on you to memorize things. I'm giving you 2 hours. To be perfectly honest, the quiz is doable in 20 minutes. Okay? So do not feel rushed. Use the resources you are allowed to use and think. Okay? So don't forget to do that sometime today. I will not grade late work on a quiz or test. You have to have your work uploaded to Blackboard as a PDF, please, no later than 11:59 tonight. Okay, is that clear? That's how we will do quizzes. And that's how we will do tests, and I will give you even more time on tests. Same exact. Book and notes. The quiz problem, I think I've said this before. I took one of the Wiley Plus homework problems that was due last night, and I tweaked it and massaged it a bit and changed it up a little bit. That's to see if anybody's just trying to memorize the solutions. That's not learning physics. Let's be clear about that. Not interested in giving you points if you can just memorize things. I want you to be able to show me you understand. That's the whole purpose. And it's meant to help you because I'm showing you where the bar is. This is where you got to be able to get. All right. And sometimes we need a little help realizing, oh, I guess I need to study a little more maybe. You never know until you see these assessments and how they go. If it's a notebook with this class content, yes. Okay. Yes, but the honor system would say nothing, that's your notes, so that's okay, but nothing else online. Right? Yeah. Yes, you may have your notes in digital form, that's okay, right? But your notes in whatever form they are in, and Wiley Plus. It's based on one of those problems, but if you've done the Wiley Plus, you know that all those problems usually have a subparts. So you can expect that. Okay. I will be able to, at various points during the day, answer emails of clarification, but I will not tell you how to do any of the problems. Okay. Okay. I have a lot I want to do today, so let me pick up now. First, I've written on the board the famous constant acceleration equations that I mentioned briefly at the end of class on Wednesday that you have had video lectures talking about, multiple video lectures, in fact. And we do use these pretty frequently, but watch out, remember the big caveat, you cannot use these equations unless you know that the particle's acceleration is constant. And one of the most common mistakes with these equations is to use them in a situation where the acceleration is not constant. That's incorrect physics. Okay? I number them 1, 2, and 3. The velocity equation, the position equation, and another velocity equation that has no t, the no t equation. Those are the only 3 I ever need to solve a constant acceleration problem. Now what I want to do is a Wiley Plus type problem that is going to require us to use them. And I'm picking one that's a bit on the challenging side to do as an example, because I want to model for you how physicists think about real world situations. And not to scare you, but to make the point upon you that there's a pretty big gap between just being able to write these equations down and understanding how to use them correctly. And the only way you bridge that gap is practice. So here's the example problem I want to do. It's based on what could be a plausible real world scenario. Sorry about the glare here, but I only want this up momentarily. Okay, we're at a major airport where it's a foggy day and it's busy. And the same runway is being used for takeoffs as well as landings. That happens at airports. Of course, the point though, the object is that you don't have a takeoff and a landing happening at the same time on a runway. But something has gone wrong, and that's exactly what's happening in this problem. 2 planes on the runway, 1 taking off, 1 landing. This doesn't sound good. Here's the rest of the information. All right, this is airplane number 1. It's just landing. You don't have to be an artist, that's an airplane. Okay, that means it's moving. And it's just landed at the origin of an x-axis. Okay, because this is what we're going to call our t=0 picture. And we are told that its velocity is plus 75 meters per second. This one. Okay, well, it is an airplane that's just landed. Okay, we also know that it can slow down with an acceleration of magnitude 1.50 meters per second squared. Read those words carefully. Can slow down with an acceleration of magnitude 1.50 meters per second squared. The second aircraft, plane number 2, has an initial velocity of 0, because that's the one that was about to start to take off. Okay? And it can speed up with an acceleration of magnitude 2.50 meters per second squared. And there is a distance L in this instant between them, between this one where it just landed and this one where it started to move. Ready with me so far? First part, we're going to make a sketch of the position of each aircraft as a function of time, x versus t, for each one on the same axes, okay? And we want to do that for the case where a collision between the two aircraft is just barely avoided. The closest you can get to disaster without having a disaster. And then after we draw the picture, we have to compute that value of L. That's the minimum safe L. Okay? What is that minimum L value between them that avoids a disaster? I do this one, again, because it's challenging, but of the level of which we want you to be able to solve problems. Okay? And it's also one where you have to draw, I contend, a picture to make any progress. So let's start this example in part A by drawing the required sketch. Here, I'm not worried about, I have labeled my axes with X and T. I'm not worried about units and so forth like that. It's a sketch, not a graph. Just want to see the shapes. Now, if I'm plotting X versus T, do I know that these particles have constant acceleration? There is a clue in the wording of the problem. You know what the clue is? The fact that they give you a number for each, yes? A number. That must be the number of the acceleration for each plane. So yes, we notice it didn't say it outright. You had to infer it. But the acceleration is constant, so these equations are going to be valid. If I'm supposed to sketch X versus T, which one of the three do you want to be focusing on? The second one, right? The X equation. Look at that equation. What would your algebra teacher call that equation? What kind of equation is it? Quadratic. When I plot it, what shape do you think it's going to be? Parabola. Okay? But I got to plot it twice, right? One for each airplane. Let me do plane number 2 first. That was the one that was taking off. Okay? So this means time 0. What's the X for plane number 2 at time 0? The one that's taking off. It's L, isn't it? Right? So we're up here somewhere at L on the x-axis. You said it's a parabola. Does it open up or open down? Those are your options. What do you think? Is it a parabola that curves up this way or curves down that way? Up, right? And is it starting at a minimum or is it starting somewhere else on its curve? You're thinking, how am I supposed to know that? Oh, but we do know enough physics to know that. Well, so if it's a parabola, you told me it's going to go up. So it's either going to be at a minimum, starting going up like that, or it's already going to have some curvature going up. I contend you can tell. Because the slope of the tangent line on this graph represents what? Velocity. What's the initial velocity of plane number 2? 0. So it must be at the bottom of the parabola where the slope is 0. And then just curve up so that the slope just gets more and more positive. Yes, it's the plane that's taking off. Now, and let's label, right? If you were drawing this for work for me, I would want you to label. Okay, plane 2, which is initially at x equals L with 0 velocity. All right, let's start with, let's next go to plane number 1. That's the one that was landing, or is landing, okay? Where is it located at time 0? What's its x? Okay, and it's a parabola, right? So it starts down here. Does it open up or open down? What's that? Well, if it opens up, then what's happening to the slope of the tangent as you go up? Getting bigger, isn't it? Is that what happens with a landing airplane? It goes faster and faster? No. So it actually has to slope. What do you mean? You mean like this? Like that? Kinda, yeah. But we'll start something like this, right? It comes up like this and starts to curve like that. Notice it's got to have a positive slope at the origin because it has a positive velocity, doesn't it, initially? Okay, now we got several options. Let me go over here and sketch them. There's the plane number 2. Now we started plane number 1. That's 2 and that's 1. If that's the graph, do they collide at all? How do you know if they collide with that graph? What do the curves do? They cross. Yes. Okay. Do those cross? No, of course not. No problem with that scenario. What about that one? Oh, that's bad. Right? Now, what do we want? We want the scenario where they just barely miss, or actually, I should say, just barely hit. All right? They glancingly touch. Think of it that way. Just the slightest of touches. How would I then draw? I get to adjust how I draw curve 1 here. So how should I draw it? You see what I'm getting at? The curves have to do what? Somewhere. Barely touch. Okay? So let's see if we can get that to happen. Something like that. See what I'm saying? Where that's plane 1. All this we have to be able to figure out. Now they glancingly touch here. So yes, they are at the same x, but just it's so glancing that everybody's fine. Nevertheless, that clearly is the most critical moment, isn't it? When everything is, oof, that's as close as it's going to get. So I'm going to label that time value TC. C stands for critical. That's the critical time. All right, so the point of this graph that I contend, and I contend also that most people won't solve this problem correctly if they don't draw this picture and look and think about it. If this is my scenario where the collision is just barely avoided, what can we say about the two planes' motion at the critical moment? T equals TC. Look at those two graphs. Look at the time TC. Tell me what you can about them. Is anything equal for the two? The x values are equal, aren't they? Yes? But that's not all. How do I get that? They must have the same velocities also. Look at the picture. If they glancingly touch at that one point, don't they share a tangent line? That's what glancingly touch means. And what's the slope of the tangent line for x? Velocity. So not only must they have the same x value, they must have the same v. in the case where they just glancingly touch. Okay?
I mean, I understood that by looking at the graph, or so like, why would they have the same velocities?
We're saying that we are going to pick this L, because this L is adjustable. We're going to pick this L so that this is what happens. Okay? The L is the key thing. If the L is too small, cross, bad. If the L is really big, they don't even get close to each other. Probably good, but that's not what I'm interested in. I want the L that's just so they glancingly touch. Okay, here we go. How are we going to, so that's part A, by the way. That's part A. Part B, find the L for this picture. Okay, we're going to use the constant acceleration equations. Doesn't that seem right? Let's start with the x's. Okay, so let's use x equals x initial plus v initial t plus 1/2 at squared. But now here's the other thing that makes these problems challenging. Often you'll have more than one particle to deal with, right? I have two. So I've got to do what I call bookkeeping and keep track of all my symbols because I have a lot of them. There's an x value for plane 1 and there's an x value for plane 2. So I need to use this equation for both. And I like to start with the equation and see if any of the constants in the equation, in this case x0, v0, and a, are 0, because that means I can just throw those terms away. All right, plane number 1 is the one that's landing, remember? So let's apply this constant acceleration equation number 2 for the first plane, this one. Are any of these constants in that equation equal to 0? The x initial, right? But not the v initial and not the a. So you can write this out, but you don't need to write that term. So now look how I'm going to write it. V01 times t plus 1/2 a1 times t squared. You see I put a 1 on them? Because this is plane number 1. Let's come over here to the side and put values for the things. Let's remind ourselves, what was v initial for plane number 1? It's hard to read. There it is, plus 75. So plus 75 meters per second. What's the acceleration for plane number 1? Again, I know it's slow with an acceleration of magnitude 1.50 meters per second squared. So I'm asking you what to put for A1. Careful, it's tricky. Negative 1.5 meters per second squared. You must see to do that, to write it that way. Why negative? Because I know the plane is slowing down, yes? Right? It's the plane that's landing. Got to keep track of all this. It's slowing down. If it's slowing down, I know velocity and acceleration must be in opposite directions. I already know the velocity is positive, so the acceleration must be negative. That's the correct thinking. Now let's write the x equation for plane 2. Okay, back to the generic equation 2. Any of those constants, x0, v0, and a, equal to 0 for plane 2. That one, remember, is the one that was taking off. Somebody said it. The initial velocity, v0. Yes? So that means this term right here can be ignored. It's 0. What's the x0 for plane 2? L. So the first term is L. The v0t term is 0, and then I'm left with plus 1/2 a2 t squared. Let's write down what the a2 is. I'm told that that plane can speed up with an acceleration magnitude of 2.5 meters per second squared. So what do I write for A? Positive 2.5 meters per second squared. The signs on those A's are both very important. How do I know A2 is positive? That's the taking off plane, right? It's got to be moving in the plus X direction and speeding up. Okay. Now, we've written down the X equation for each one. Let me go ahead now and write the V equation. V equals V initial plus AT. We got to do that for plane 1, V1, and we've got to do it again for plane 2, V2. But again, take the generic one, generic form of the equation, look at the constants, in this case V0 and A, see if either one is equal to 0. That would simplify things. All right, again, plane number 1 is the one that was landing. Is its initial velocity 0? And its acceleration is not 0. Neither are 0. So all we can write here is V initial 1 plus A1t. Use symbols, please. Don't write in these numbers. No physicist or engineer does that at intermediate steps. Use symbols. You plug in numbers at the end. Okay. Now, what's the V2? Can it simplify any? Which term can I drop? V initial. It has an initial velocity of 0. So the formula for V2 is simple. A2 times T. Well, I got 4 equations. Bit to deal with. But remember, at the critical moment, but only at that moment, no other time is it true, but at the critical moment, the x1 equals x2 and the v1 equals v2. Yes? So let me now apply that. Let me set the v formulas equal. This is only valid at that special moment, t critical. So when I set the v equations equal, this is on one side and this is on the other. But the t must be labeled tc, because that's the only time when they're equal. V initial 1 plus A1 T critical must equal A2 T critical. Any thoughts on what you might do with that equation at that point? Can you learn the value of something from it? TC? Don't you know everything in that formula except for TC? Well, let's solve for TC. It's not the answer to the problem, but it might be helpful to know it. Now here you have to be able to do the algebra. Notice 2 terms with TC. So take this term over, it picks up a minus, factor the TC, and you'll have in parentheses an A2 minus A1. See what I did? You got to be able to do that algebra. Then divide both sides by that quantity in parentheses, and you have a formula for T critical. V initial 1 over A2 minus A1. And yes, if you want, you could plug in and get a number for TC, because you know all these numbers, right? This is 75 meters per second. This is 2.5 meters per second squared minus, watch out, negative 1.5 meters per second squared. You can't drop that negative sign when you plug in the value of A1. I will tell you what you get, although I didn't need to know it the way I did the work, but I will tell you, the T critical moment is at 18.75 seconds. Okay. Remember what I'm supposed to solve for? The L that makes this picture happen. Well, it must going to be from setting the x's equal, yes? x1 must equal x2. So take the x equations and set them equal, but put in T critical. So V01 T critical plus 1/2 A1 T critical squared equals L plus 1/2 A2 T critical squared. Don't I know everything except L? Look at all the symbols. Just go systematically. I know V initial 1, I know A1, I know A2, and I just found T critical, didn't I? So I know everything but L. So solve that equation for L. To do that, all you got to do is take all that blob right there over to the other side. And it'll change with a plus in front of it to a minus. Let's write down what it looks like. I'll write it in the form L equals V initial 1 TC plus 1/2 A1 TC squared minus 1/2 A2 TC squared. I'm inclined to do a little factoring here. Let's factor a 1/2 and a TC squared. Looks like that. See what I did? I just did some factoring. Now, at this stage of the game, if you want to just plug in the number for TC, you can do that, yes? And the V0 initial 1, and the A1 and the A2, you can do that. And you will get your answer. I will just show you, not that I expect you to do this early in the semester, but I want to show you a skill that I want you to develop as the semester goes on. It's called algebra first, before numbers. You solve symbolically for the desired quantity and then plug in numbers. How do you do that? Let's mark the TC equation with a star. All I'm going to do is substitute equation star for TC. I get L equals V initial 1 times TC. V initial 1 over A2 minus A1 plus 1/2 A1 minus A2 times T critical squared. V initial 1 squared over A2 minus A1 squared. You see what I did? I'm hoping that this simplifies some. Don't do your algebra first and then just stop if you haven't simplified. Let me show you a trick. You see that A1 minus A2 and that A2 minus A1 squared? Those are almost the same, and if they were exactly the same, I could cancel that with one of those powers. But I can get them the same. Just factor a negative sign out front, like that. Then this becomes A2 minus A1, right? If you do that, that whole term cancels one of those. Now let's see what this looks like. L equals, look carefully at this first term. There's V01 times V01. V01 squared, and the denominator is A2 minus A1. That's this. Minus 1/2 times what's left here. V01 squared over A2 minus A1. Now again, let's strengthen those algebra skills. This might look weird, but look at for patterns. Complicated blob minus 1/2 of the same complicated blob. Yes? What's blob minus 1/2 of blob? 1/2 of the blob. So the final answer is V01 squared over 2 times A2 minus A1. That's what's called the symbolic answer.
Sorry, what if we just like from that page without substituting equation? Why don't you just put the numbers in?
That's right. So that's what everybody wants to do initially, put in numbers early, okay? But what a physicist or engineer wants to have is the symbolic answer, because now that I have the symbolic answer, I'm not tied to these particular numbers. Maybe the V initial 1 is different. Maybe it's 80 meters per second. Or maybe one of these numbers is different. I just plug in the numbers into that formula. And I can see how the L depends specifically on those formulas. For example, I see that it depends on V initial 1 squared. But if you plug in numbers early on, then from that point on, you are only solving the particular problem with those values. See what I'm saying? So you get much more bang for your buck if you solve symbolically first.
Sorry, why do I stop like L equals V naught, like something V naught Y plus this, like that line?
This line.
Yeah.
That's what I'm saying. It's too early. You want the final symbolic answer in terms, all of those were given numbers. You want, the symbolic answer must have only in it quantities that were given in the wording of the problem. Now you plug in numbers and you get 703 meters. Yes.
But with all problems that we're going to be doing, at least in this semester class, will we be able to solve for symbolic answer?
Yes. However, there may be some times when even I would say, you know what? The algebra to do this symbolic solution is doable, but will be so messy that the effort won't be worth it. Now, that will not be the majority of the time. Most of the time, I will solve symbolically.
So if we are solving and we have to decide between just plugging in the numbers and solving algebraically, how do we make that decision? How do we know if it's going to end up complicated or not?
Yeah, that really only comes from experience. So my advice would be, especially here at the early on, don't beat yourself up too much if you can't see how to do it symbolically. Just use the numbers. But every once in a while, try. So let me try to see if I can just solve for the symbols. And then push yourself to try to see if you can do that more and more. Okay? But you'll really only know if you try.
Is there a standardized way of writing each symbol for the stuff that we'll learn about in this class?
Yes?
We can access, like, is there a table or like
It's mainly just what I show you in my video lectures, because I take those same symbols right from the book. So the book and my video lectures are the symbols we must all agree to use.
and that's for every physicist?
For most. There's not universal agreement on every symbol used in physics, but on most, yes. But for us, use what's in the book. Okay? Like little v is for everybody means velocity, and little a for everybody means acceleration. Okay, I've got 10 minutes. So what I want to do next, let's see if I can get all this to work. Let me bring the screen down because I know that that's not very helpful there. So I hope you had a chance, I know it was long, to watch today's video lecture. It was long because the content is so important. Okay? As I said in that lecture, it's probably the most important content for the whole book. It is about what we call vector algebra. And how do you correct mathematics manipulate vectors? Okay? So these are all the various things that we need to be able to do in this section of the book. This is chapter 3, section 1. We have to be able to add vectors by actually drawing arrows in the head to tail configuration. We need to be able to subtract one vector from another in using arrows. We need to be able to calculate the components of a vector on a given coordinate system and show them in a drawing. This is probably the most important learning objective in the entire class. And I really do mean that. You must be able to do that calculation in any scenario we might give you. Given the components of a vector, draw the vector and determine its magnitude and what you call its direction. That's also important. That is probably the second most important learning objective in the whole book. And then convert angles between degrees and radians. I know you know about degrees. Probably at some point have learned about radian. For now, you just note that your calculator has a degree mode and a radian mode. You choose the mode that you want. We'll do mostly degrees, okay, for this chapter. Let's start practicing. Again, I talked about all the things that I just showed you, learning objectives, on my lecture video. So now we just start practicing with vectors. And the first practice I want us to do is to take two vectors given graphically, drawn as arrows. There they are. They're called D1 and D2. There's just some generic vectors. I don't even know what they represent. Something that's a vector, maybe a displacement. Doesn't matter. So they could be velocities, they could be accelerations. Those are all vectors. Just two vectors, D1 and D2. You see how they're drawn? You see why this is called head to tail arrangement? Tail, head. The head is the point. The other end is the tail. Clearly, those are head to tail. Okay? All right. You can see they lie in an XY plane. Here's the first question. What is the sign of what we call the X component of what you get when you do that vector sum, D1 plus D2? And then we'll get the sign of what's called the Y component. So I want us to talk that through. Okay? Let me draw an XY coordinate system. You can see the D1 and the D2. D1 is roughly like this. The D2 is head to tail with D1, goes up like that. Now you should be able to draw on that picture D1 plus D2. I would like you to do that in your notes, right? You got those two drawn there? Sketched? Sketch, please, D1 plus D2. Okay? How do I draw that? How do I draw D1 plus D2? Yeah. Perpendicular to the head of D2. That's a little bit.
No, I guess like to create a right triangle.
Not necessarily. I know where your right triangle is coming into your head, and it's important, but that's not what I want here. From the origin to the head of D2. Okay? In other words, from the tail of the first vector, D1, to the head of the second, D2, like that. That's head to tail vector addition. The resultant goes from the tail of the first to the head of the second. So that green vector is D1 plus D2. Everybody see that? That's the first thing you got to be able to sketch for yourself. Now, to answer this question, I have to find the X and Y components of D1 plus D2. To be more specific, they are called the X and Y scalar components. This is where the right triangle comes in. Focus on the green arrow, okay? That's all I'm talking about now, the green one. Let's sketch the X and Y scalar components for that green arrow. You want to try that on your paper? How do you do it? That's that most important learning objective, right? In the whole book. You see the green arrow? You see how it's drawn? Sketch its X and Y scalar components right on the picture. I'm going to draw a new picture just beside the first one with less stuff. Specifically, just D1 plus D2, okay? All right. How did you draw the components for that green arrow? Let's put somebody else. Anybody want to answer who hasn't answered yet? Yes, Adrian. head, okay, and do what? I just dropped a perpendicular for vertical. Okay, so tell me now how to draw the X and Y components. Got to be able to draw them. You see did you see the pictures I showed in the lecture?
You put the more simple arrow on the top of that one. So it's not face off.
Okay, yep, we're going to draw arrows like this. Just plain arrows. How many of those do I have to draw? 2, 1 for each component. Scalar component. Let's do the X one first. Thoughts on how to draw the X scalar component?
We draw from the where x equals 0, and then you draw on the left where it meets that one.
And you put an arrowhead on it. Okay? That's called, if you want to be fancy, the projection of the vector onto the x-axis. If you shined a light very far away, straight down, that'd be the shadow on the x-axis. It's plain old arrow. You must draw it to the left. Why? Because the vector itself, look at it carefully. It points to the left and up. You understand what I'm saying? So the x component is to the left and the y component is up. Components are determined by the vector. So the y component, now you have to be able to draw that on this same picture. Start right here and go right along y with an arrow until you get to the head. And that's the x component and that's the y component. The result you see is a right triangle. And I want to see the little arrowheads on the components because they're telling you the sign of that component. Okay? For example, what's the x component of d1 plus d2? Just the sign of it. Is it positive or negative? It's negative because the arrow points in the negative x direction. And what about the y component? It's positive, right? Because that arrow points in the positive y direction. Let's do one more. What's the sign of the x and y component for d1 minus d2? Now I'm subtracting one vector from another, aren't I? Let me clear out part of my picture here. There's d1. How do I do d1 minus d2? Yeah, you know. Take d2. What this really is saying add. Add d1 plus negative d2. Okay? Take d1 plus the vector negative d2. If I draw a picture of a given vector like d2, how do you draw negative d2? You just reverse the direction, right? Don't change the magnitude, just reverse the direction. So you got to be able to look at the d2 and say, well, the negative d2 would be roughly like that. You see how I just looked at that? Just draw that arrow, but reversed in direction. d2, negative d2. Still got to draw these two head to tail because it's still vector addition. Now draw the resultant, d1 plus negative d2. Should be able to draw that on or sketch that on this picture because it's still vector addition. So you draw an arrow from the tail of the first to the head of the second. And that's d1 plus negative d2. Now notice then, Focus now only on the green arrow, just the green one, because that's the resultant. Notice it points down and to the left. Yes? So the x component must be to the left, and the y component must be down. You can draw them if you want. All right, I'll do that and then I'll stop. There it is. There are the axes. There's two ways you can draw these things. You could do it like this, and then go like that, and like that, for example. You always end up with a right triangle with the components as the legs. Now look at the arrows. The x component is to the left, the y component is down, like I said. That tells me the x component is negative, left, and down for the y-axis is also negative, right? So this vector's x component is negative and its y component is negative. This one you can try on your own. What are the x and y component signs for d2 minus d1? On your own, when you have time, if you want to practice, okay? We are out of time for class, though.
This one's more of an algebra question.
Okay, just one second. Let me stop the recording, and then we'll be good to go.
Professor?
You're welcome.
Thank you.
Yes.
Professor?